with Chapter 3, Section 5, we really just start cementing things that we already know and filling in some details about some of our parent functions. Section 3.5 focuses on polynomial functions. Now, a polynomial function always has some characteristics. Every polynomial function has these characteristics in common. Sorry. First of all, our domain includes all real numbers. So, you know those quadratic functions that we've been working with so much, where the domain is all real numbers? A quadratic function is an example of a polynomial function. Remember that when you have a domain that is all real numbers for the parent function, once it starts all real numbers, it's going to stay all real numbers no matter what transformations we do. Our graphs have smooth, continuous curves when we have a polynomial function. So we are not going to have any breaks, we're not going to have any sharp corners, all smooth, continuous curves over the entire domain. Third thing, all terms have positive integer exponents. So the exponents, the little numbers, for example right here, I raise a base to a power. That power is always going to be a positive integer. An integer is a whole number. So positive integers are those counting numbers like 1, 2, 3, 4, 5, 6. That means that if I have a polynomial function, I will never have an exponent that is a fraction or negative. All right, fourth thing, if one function value f of a and another function value f of b both have opposite signs, so if I plug in some value a and I get out a positive answer, and then I plug in some value b and I get a negative answer, then I know that there is a root between them, a zero of the function. That's because I know that to get from positive values to negative values, I have to cross the x-axis. And then finally, the greatest possible number of turning points is no more than one less than the degree. So let's say I have a 10th degree polynomial. I know that it can turn up to 9 times because 9 is 1 less than 10. Okay, intermediate value theorem, this isn't something you're going to have to restate. This is just how we are able to graph a continuous function without finding an infinite number of function values. Suppose that I know that f is a polynomial function, and this interval from a to b is an interval where if I plug in a, I get one answer, and if I plug in b, I get a different answer. They're different things. The function value of a and the function value at b, not the same. If L is a number between f of a and f of b, then there's a number c inside that interval so that when I plug it in, I get that answer. Okay, that was really tricky. Let's put it into practice and see what it means. Here is one of our polynomial function parent functions. Hopefully when you see this, the third degree, you remember now that this is my cubic function, cubic parent function. When I plug in x, I get out x cubed. So let's just pick some numbers. We're going to do -2, -1, 0, 1, and 2. Those are kind of my 5 standard go-to values when I'm graphing a function with a domain of all real numbers, because when I have a parent function, usually whatever turning happens around the origin. Alright, if I plug in a -2 and I cube that, so I'm going to say -2 cubed, I get -8. If I plug in a -1 and I cube it, -1 times -1 times -1 is a -1. 0 cubed is just 0. 1 cubed is 1. And 2 cubed, 2 times 2 times 2 is a +8. So these are my function values for each of these x values. Let's graph our cubic function. So where I have x is -2, y is a -8. So that's 5, 6, 7, -8 right there. Where x is -1, y is -1. Where x is 0, y is 0. There's my turning point. 1, 1, and then 2, +8. 1, 2, 3, 4, 5, 6, 7, +8. So here's my parent cubic function. Now notice what I'm doing right now. I have 5 points that I know the location of, but I just connected and made a continuous curved graph. Well, how did I know I can do that? I know I can do that because of the intermediate value theorem, IVT. It tells me that, okay, I know that -2, plugging in -2 gives me a function value of -8, and I know that plugging in a -1 gives me a function value of -1. I know that if I pick any number between -2 and -1, let's say -1.5, -1.7, that is going to give me a function value that fits between those function values. If I pick a value between 0 and 1, let's say I pick 0.5 and I cube it, 0.5 cubed. Well, I know that whatever this is, it's going to be between 0 and 1 here, because I know that I'm going to end up with a point right there. So I know that whatever values I choose on my x-axis in my domain is going to correspond to a y value that will fall between the other y values. That's what allows me to have that continuous graph. Okay, degree of a polynomial function. We referenced our degree of a polynomial function over here when we said that the greatest number of possible turning points is no more than 1 less than the degree. Well, what is the degree of a polynomial function? It's just the value of the largest exponent on a term. When I am listing the terms of a function, I should put them in order. Sometimes my math lab will mess with you and not put them in order, but the terms should be in order, where I have the largest exponent first and then the smallest exponent last. And I'm going to watch for that highest exponent. Because that highest exponent signifies where my leading term is. So we're gonna hope that the function terms are listed in order. For example, in order, I would have 3x to the 5th plus 7x squared minus x minus 3. Is this a polynomial function? Well, my exponents are all positive integers. The exponent on this x would just be 1. It's understood. Positive integers, so that works. All terms have positive integer exponents. My terms are in order. My largest exponent here is 5, and then 2, and then 1, and then this would be x to the 0 power, would be my power on that term, because it's just a constant. The degree of this polynomial function is 5. It's equal to the highest exponent. Now, what does that degree tell us? It tells us a lot of stuff. Oh my goodness, it's been a long day for me. It tells us the maximum number of turning points. It also tells us we are able to expect, however, whatever the degree is, we are able to expect that many total, M-A-N-Y, that many total roots or zeros for my polynomial function. So where I have degree 5 here, I expect a total of 5 roots. Now they don't all have to be different. Some could have a multiplicity greater than 1, and we're going to talk about that here later on. Let's do another example. Watch out for that highest exponent. Remember, I warned you that sometimes my math lab messes with you just to see if you're paying attention. In that case, it's not necessarily going to list your terms in order. So this looks like polynomial because my exponents are positive integers again, but my first term is not the leading term. This would be my leading term here. This would be my leading term because it's the term with the greatest exponent, not just because it's first. This is not the leading term of g of x. This is the leading term of g of x. That's my leading term. It's out of order. My leading term is a -8 x to the 6th, so the degree of this polynomial function is 6. The degree of this polynomial function is 6. Now, maximum number of turning points. Remember, that was one of our characteristics. The maximum number of turning points is equal to, or up to, the maximum number tells me that's the most. So it can turn up to 1 less than the degree of the polynomial function. So this polynomial function with degree 5 can turn up to 4 times. This polynomial function, degree 6, can turn up to 5 turns. So if I say I was going to go at it backwards, let's say that I have a polynomial function, and my polynomial function, we'll do this. Polynomial function looks like this. What degree could this polynomial function be? Well, how many times does it turn? Here's a turn. It's going up, it turns and goes down. Turns and goes up, turns and go down, turns and goes up. Has 1, 2, 3, 4 turns. Since it has 4 turns, it has to be at least 5th degree. It could be 7th degree or 9th degree, but it can't be a 3rd degree polynomial. Cannot be a 4th degree polynomial. It has to be at least a 5th degree polynomial. All right. Let's look at the next page of our notes. Talking about end behavior. Now this function that I just sketched, it's got some interesting bits going on here where I've got hills and valleys, I've got turns, but most of the function exists at these ends where it goes on toward infinity. It either goes down or up forever and ever and ever towards infinity. That end behavior is where most of my function happens. Because the domain of a polynomial function includes all real numbers from negative infinity to positive infinity, all real numbers. Most of the function exists to the far right and left as the function gets large. As it increases, rises, or decreases, falls without bounds. My leading coefficient test allows me to predict my end behavior for my polynomial function. We have to examine the leading term of the function when the function is not factored. Now I circled those leading terms. The leading term is the term with the largest exponent. A leading term has 3 pieces of information. It has a coefficient, a base, and an exponent. A coefficient, a base, and an exponent. Right here, coefficient, base, exponent. So let's examine leading terms when the function is not factored to see what is going on with our end behavior. Now that leading term, like I said, has a coefficient. Leading term has a coefficient, has a base, and it has an exponent. 3 pieces of information. That coefficient is either positive or negative. Either going to have a positive coefficient or a negative coefficient. And that degree, that exponent, is either going to be even or odd. So we're interested in the coefficient and we're interested in the degree. An even degree exponent would be an exponent of 2, 4, 6, 8, all even numbers. An odd degree exponent would be 1, 3, 5, 7, and all those odd counting numbers. Because remember, my exponents are always positive integers. Well, what happens? If the degree of the function, that exponent, that largest exponent, is even, an even number, 2, 4, 6, 8, the ends are going to even out. Now, if they even out, they're going to go together. So either both ends are going to go up or both ends are going to go down. If I look at this function, these ends do not even out. One goes up, one goes down. But when I think about my parabola, ta-da, both ends go up. Or if I have a negative out front, that parabola, both ends go down. So there is our key as to which way we're looking. If it's an even degree and it's positive coefficient, both of those ends go up. Now don't have them connect in the middle because we don't know what's going on in the middle. We just know that the ends are both going up if it's even degree, positive coefficient. If it's even degree and negative coefficient, then it flips it and both ends are going down. Don't draw a parabola here. It may not be a parabola. It just means that both of those ends are going to be headed downward no matter what happens here in the middle. Well, odd degree polynomials. We've got 2 odd degree polynomials here. This one was my cubic function. This one would be, I said, at least a 5th degree polynomial. One end up, down, one end up. So odd degrees, they are odd. One goes up, one goes down. Those go in odd directions from each other. If it's positive coefficient, if this number in front of my base, this is positive and the degree is odd, then that means if I were to take the ends and pull them straight, it would be moving in a positive direction, increasing function. So for an odd degree positive exponent, I start low and I finish high. If I were to straighten that out, I would have a positive or an increasing slope. Conversely, if it's odd degree and a negative coefficient, it's going to start high and finish low. Don't connect the ends. If I pulled this straight, I would have a decreasing function, a negative slope. Okay, so let's do some examples of this. We're going to first determine the leading term. And as I look at my 4 examples here, I see that they're all in order. All the terms are in order. So I can circle the first term for each of these, and I've circled my leading terms. Now notice when I circle the leading term, I circled a coefficient, a base, x, and then the exponent on that base. All right, so end behavior. I'm going to sketch one of these 4 shapes. Oh, this is a cubic function, and my coefficient is positive. So it's going to look like my parent function as far as the end behavior goes, where I start low and finish high. The degree of this is 3. So that tells me that the most turns that my function can make, it has to be 1 less than this degree. So it's going to be less than or equal to 2 turns. And my 3 tells me that I'm going to have 3 total roots, or zeros, places where I intercept the x-axis. Okay, let's do one more together, and then I want you to pause and do the last 2, trying to see what you can puzzle out on your own. Again, my exponent is odd, so it's going to be one of these 2 end behaviors. One end goes one way, the other end goes the other. My coefficient here is negative. It's a -8. So if it's odd degree and a negative coefficient, I start high, finish low for my end behavior. Let me change colors here. Start high, finish low, not connecting the dots because I'm not showing you the entire function, just which way the ends go. Well, what is this degree? This degree is 5 because my largest exponent is 5, which means that I'm going to have less than or equal to 4 turns, 1 less than that degree, and a total of my degree, 5 total roots, or zeros, places where I intercept the x-axis. Okay, pause your video, try the next 2, see how you do, and then restart to see if we agreed. So for the next one, f of x, my leading term is 9x to the 4th. That's an even degree, a positive coefficient, so both ends are going to go up. For that degree of 4, since my degree is 4, 1 less than that is 3. So I'm going to have less than or equal to 3 turns. So up to 3 turns, and my degree, 4 total roots, or zeros, for my function, places where the graph intercepts the x-axis. And finally, this one is even as far as the degree and negative for the exponent. Even and negative means both ends are going to go down. So sketch my end behavior with the ends not connecting. Degree here is 8, which means 1 less than 8 is 7. Up to 7 turns, less than or equal to 7 turns, and my degree is 8, so 8 total roots, or zeros, when I consider multiplicity. Alright, excellent. We're going to spend a lot of time working with polynomial functions, so make sure that you understand these definitions and how to use that leading term. Behavior at the x-intercept. So those x-intercepts, that's what we're talking about when we call, when we say roots or zeros. Those are x-intercepts, where I intercept or hit the x-axis. Every x-intercept corresponds to a factor of my polynomial function. And when I have it factored, I've got that factor x minus a or x plus a raised to the k power, where a is that value, that factor, that root, and the multiplicity, the exponent, is k. Now, if that exponent, that value k, is odd, the graph is going to cross the x-axis at that root. If that exponent is even, the graph is going to touch and turn at that root. And how can you keep it straight? Well, even, touch, and turn, 2 t's. Even numbers are divisible by 2. All right, let's take a look at it. Now, this particular function, sorry, I hit the focus button. This particular polynomial function is given to me in factored form, so I cannot just look at it and see what the leading term is. I have to do a little bit of work, a little bit of thought. I have to think about if I were to multiply everything together. Now this x minus 5 squared means that I have x minus 5 times x minus 5, and then I have x plus 4. So I've got 1, 2, 3 total factors. If I were to multiply all of these terms together, well, you know, if I were to FOIL these two, x times x is x squared, right? And then if I take that x squared and I multiply it times this x, I would have x cubed. And none of those have a coefficient other than 1. So my leading term is x cubed. What's the shortcut way to do that? Well, all I have to do is add up my exponents to figure out that degree on my leading term. My exponent here is 2. The understood exponent on this factor is 1. 2 plus 1 is 3. So if I multiply all this together, I've got x cubed as my first term with the largest exponent, and there is not a coefficient out front. So my coefficient would be 1. It's understood to be 1. We don't write these ones in, we just understand that there's just one of them. So leading term, x cubed, 1x cubed, 1 is positive, 3 is odd, so my end behavior for a positive coefficient, odd exponent, odd directions, and it goes from low to high. It's already factored for me, so I'm going to first, well, degree in behavior, maximum number of turns. So degree is 3. My maximum number of turns, that means less than or equal to 2 turns. It's not going to turn more than 2 times. Let's find, before we sketch the graph though, and I didn't put this in my list of instructions, but you have to do it. It's already factored. I want to take each of those individual factors and set them equal to 0. So if I do x minus 5 equals 0, that gives me x equals 5 as my first root. And if I do x plus 4 equals 0, I get x equals negative 4 as my second root. Those are my roots, or my zeros for my function. And I need to check their multiplicities. Well, for this factor where I get the value 5, that multiplicity, that exponent is 2. So it's got a multiplicity of 2. My even multiplicities, the graph is going to touch and turn at that value. X equals negative 4 comes from this root. The exponent is 1. That's odd, so the multiplicity is 1. And the graph is going to cross at that root. So we know that my graph is going to intercept at 1, 2, 3, negative 4, and 1, 2, 3, 4, positive 5. Negative 4, positive 5. I know it's going to touch and turn at 5, so I'm going to put a little t there to remind myself. And I know it's going to cross at negative 4, so I'll put a little c there to remind myself about that. Now we also want to kind of stop and think about what my y-intercept would be, because that gives me more information for my graph. The y-intercept happens when x equals 0. So if I do f of 0 here, I have 0 minus 5 is negative 5 squared times 4. Well, negative 5 times negative 5 is 25, times 4 is 100. So my y-intercept is, and I'm going to show that I've got a break in the graph, way up here at positive 100. My end behavior, start low, finish high. I need to make sure I include these x-intercepts, these roots, and include this y-intercept. So if I start low, I come up and I cross I'm going to hit that 100. I'm going to need to turn around somewhere, come back down, touch and turn at the value x equals 5. So our end behavior was important. Our behavior to our x-intercepts was important. I don't know exactly how high this goes. We don't care right now. What we care about is where I have a hill, where I have a valley, between what x-intercepts. All right, let's look at the next one. This one is factored, so I cannot just look at it and see the leading term. I have to think about what would happen if I multiplied it all back together. I've got 3 separate factors, so when I set those factors equal to 0, it's going to give me 3 separate roots. And I can't talk and write at the same time today. Okay, let's try this again. So x plus 5 equals 0, x minus 3 equals 0, and x plus 1 equals 0. That's going to give me my roots. Exponents, 3, 2, 1. 3 plus 2 plus 1 is x to the 6th. None of these x's have a coefficient other than 1, so that's my leading term. That gives me a degree of 6 up to 5 turns. And my end behavior, it's positive and even, so both ends are going to even out. They're both going to go up. So there's my end behavior from that leading term. Okay, my roots to put on my graph and their multiplicities. When I take this first factor, x plus 5 equals 0, set it to 0, I get a root at negative 5. Multiplicity 3, that's odd. So it's going to cross at that root. X minus 3 equals 0 gives me a root at positive 3. Multiplicity is 2, so that is going to touch and turn because that's an even multiplicity at that root. And then if I set this equal to 0, I get x equals negative 1. That exponent is 1, multiplicity is 1, so it's going to cross at that root because 1 is odd. The other thing I need to think about is my y-intercept. Where x is 0, what is y? So g of 0 would give me 5 cubed times negative 3 squared times 1. 5 times 5 is 25 times 5 is 125. 125 times negative 3 is 9. 125 times 9 comes out to be 1,125. So these were kind of ugly y-intercepts, right? So that y-intercept, again, I got to say, oh, I got a break in my graph. Way up here somewhere, I got 1125. My x-intercepts happen at negative 5, where I'm going to cross. Positive 3, where I'm going to touch and turn. And negative 1, where I'm going to cross. And I do those little letters on my graph to remind me what to do as I come in there and connect my points. All right, ends, both ends up. So I'm going to start high, I'm going to finish high. Let's see what we got. So we're going to start up here, we're going to cross, we're going to cross, we're going to go way up there, come back, touch and turn, and then go up again. Both ends are going up. So I know that I've got a minimum here, but I don't know how low it goes. And I've got a maximum here. This maximum is probably up there somewhere because those that's a relative maximum. It's a hill. They're usually kind of balanced out between the roots. And one root here, one root there. Probably that max is going to be kind of in the middle over it. I don't know exactly how high it goes for this hill. I don't know exactly how low it goes for that valley, but that's okay. I know the general shape of my graph. Now remember, this is our introduction. This is where you get introduced and you start getting a grasp on the concepts. We will work on this more through homework, through class. If you meet with me in class, you can always meet with a tutor to ask questions about these concepts and to practice them. My math lab is a great place to practice. So, something important to remember, if you have a root with a multiplicity, so k value greater than or equal to 3, that's going to cause that graph to flatten out at that root. It doesn't change what happens, it just changes how it looks. So we're going to look at some examples of this. My parent function f of x equals y squared. That's my parent quadratic function. Looks just like that. Opens just so. My value here, k is 2. Here k is 4 at my root 0, so it's still going to touch and turn, but it's going to flatten out. So it's not just going to come down, go back up. It's going to come down, it's going to kind of slow down, flatten out, widen out at the base. Doesn't get completely flat, but it gets much wider. You compare the difference. This one flattens out where it comes in to turn. You can see it, I think, even better with our odd multiplicities. Here, k is 1, k is 3, k is 5. These two are parent functions. This is my parent linear function. We know that that just shoots across with a slope of positive 1. This is also going to cross, but this is my cubic function, and it doesn't just shoot across, does it? It takes kind of a pivot there. It slows down as it comes into that intercept at 0, and then it kind of gives a little wiggle. As I keep going up on my multiplicity here, 5 is still odd. It's still going to have the same general behavior, but it's really going to come in and slow down. So as it comes into 0, it's really going to slow down, gets a lot, does not get flat, but it really slows down and starts to kind of flatten out there. So you can see that that behavior at the x-intercept is different depending on that multiplicity. Okay, let's look at a couple of these, and then we are going to be done with this guided note video. These two this function, excuse me, let's try again. This function is not factored. G of x is, but f of x is not factored. So when it's not factored, super easy to see our leading term. Our leading term is given to us. Our leading term is x to the 4th. It's positive and even. That means my end behavior, both ends go up. My maximum number of turns, because my degree is that large exponent of 4, it's going to turn up to 3 times. Turns, not times, I meant to write turns. It's going to have up to 3 turns. Could have 1 turn, 2 turns, or 3 turns. Cannot have more than that. To sketch the graph, we need to factor it, and we need to find those roots with their multiplicities. So let's factor by first finding my greatest common factor. So let's factor this. My greatest common factor between these two terms is x squared. So if I pull out an x squared, that leaves me with x squared here minus 4. And this is difference of squares. This will factor. So I've got x squared, and then I've got x plus 2, x minus 2. So I have 3 different factors here. Each of those factors results in a root. So if I set x squared equal to 0, and I take the square root of both sides, square root of 0 is just 0. So my first root is at 0. The multiplicity there, multiplicity is 2, so it's even multiplicity. It's going to touch and turn. My next root, if I set this factor equal to 0, I get x equals negative 2. Multiplicity is just 1, because that exponent there would be 1, so it's going to cross. And then I've got x equals positive 2. If I set that equal to 0 and solve for x, I would get positive 2. Again, the exponent on that factor is 1, so it's just going to cross there. Y-intercept, if x is 0, 0, 0. Anytime you have an x-intercept at 0, that's also your y-intercept, because that origin is intercepts for both axes. So I've got an intercept there at 0, I've got an intercept at negative 2, and one at positive 2. Let's look at our behaviors here. At 0, I'm going to touch and turn, but at negative 2 and 2, I'm going to cross, so I make that notation so I don't forget. This 0 takes into effect our y-intercept as well. My end behavior, both ends up, so I'm going to start high, I'm going to cross, come up, touch and turn, go back and come up again and cross, finish high. There's my graph. Alright, last example. This one's factored for us, which gives us our roots really easy, but we have to do a little work for our leading term. If I think about multiplying this back together, I've got x to the 4th and just x. Add my exponents, that is x to the 5th power. The coefficient is just 1, positive 1. So it's positive and odd, which means I'm going to start low and finish high for my end behavior. If I plug in 0 to find my y-intercept, it's negative 3 to the 4th power times 2. Negative 3 to the 4th power times 2. If I need to do, now I know that when I raise something to an even exponent, my result is going to be positive always, always. So I need to start parentheses, do negative 3 inside those parentheses, and then raise that to the 4th power to make sure that my argument has the correct sign. And then I need to multiply that by 2. So my y-intercept, where x is 0, x is 0, y is 162. There's my y-intercept. I have two unique roots. So I have x minus 3 equals 0, and I have x plus 2 equals 0. I solve here, I get a root, roots and multiplicities. My root, x equals 3. Multiplicity was that exponent on that root. That factor is 4, so it's going to touch and turn because that's even. And then my other root here, when I solve this, I get x equals negative 2. That multiplicity is 1 because that's my exponent there, so it's going to cross at that root. Alright, let's put this on the graph. X equals 3, 1, 2, 3. X equals negative 2. We've got a y-intercept way up here somewhere at 162. We know that we have a positive function moving in a positive direction, start low, finish high. It's going to touch and turn at 3. It's going to cross over here at negative 2. So I start low. That y-intercept does not have to be my relative maximum. I'm going to cross, and I'm going to come back, touch, turn, finish high. Relative maximum here, not sure how high it goes. I know that this is my minimum because that's an intercept, so I have to touch and turn there.